the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss Ohm's law and EMF. This is the first lecture in the second semester of electromagnetism. The first semester, we were focused on static fields. We were looking at electrostatic fields. We looked at dielectric medium. We looked at magnetostatic fields, fields that were generated by steady currents carried by thin wires. And we also looked at the fields due to magnetic materials. Now we're going to get into time-varying fields. Over the next coming months, we're going to be talking about waves, electromagnetic energy, the fact that fields carry angular momentum, and we'll talk about radiation. So that's what's coming over the next few weeks. However, we will be discussing Faraday's law of induction, the flux rule. We'll look at motional EMF, inductance, and also the displacement current and Maxwell's equations. Today, however, I'm going to begin with Ohm's law and EMF. And the way I look at Ohm's law is from maybe a little bit different perspective from what you're used to in your general physics class, where you just focus basically on circuit analysis. Generally, the way you begin, you start with electric fields, you talk about potential, and you figure out how to calculate the amount of energy stored in things like capacitors. But then you go down to solving circuits. There's not really a clear connection often made between field theory and circuit theory. So in today's lecture, I am going to bridge that gap. The reason why is that it's actually some of the calculations tend to be very difficult. And this is an area of active research over the past few years, which is kind of amazing to think that circuits have been around for so long and been used for so long, and yet the connection between circuit theory and field theory is really not made all that clear. Okay, but let me begin with a relation that holds for many substances. That is to say that the volume current density is proportional to the force per unit charge. And this sigma represents conductivity. It doesn't represent surface charge density in this case. So we have volume current density equals conductivity times the force per unit charge. And lowercase f represents the force per unit charge. Sigma, the conductivity, has units of inverse ohm meters. Now, Lorentz force law tells you that the force the charge experiences is equal to the electric field plus the cross product of the velocity vector and the magnetic field. Now, if we assume that the velocity is small, basically ignore that second term, and dividing both sides by q, this will give me the force per unit charge. It's just basically the electric field. So I wind up with J is equal to sigma times E. And that's Ohm's law. And again, sigma is most certainly not the surface charge density in this case. All I can say is basically it's convention that you use sigma for the surface charge density. We just don't have enough Greek letters or English letters in the English alphabet to accommodate our needs. So sigma in this case, though, represents conductivity. Okay, so when you were in general physics class, you talked about Ohm's law a great deal. And the form with which you are certainly more familiar is this one. The potential is equal to the product of the current and the resistance. And actually, I'm going to write the resistance as a cursive capital R, just to distinguish it from R representing the radius of spheres and cylinders, say. Okay. because these forms don't look the same, it might be a good idea to show you that they actually have the same content. So let's look at a straight wire that has length L. And cross-sectional area A. And we'll assume further that it is characterized by conductivity sigma. So let's look at Ohm's law over here. Current, in fact, is equal to the following current density times area, so that's just times J times A. And so therefore, I can multiply the right-hand side over here times A as well. I'm going to assert now, without proof, that the field is uniform. Okay. So if the field's uniform, that means I can immediately write down the electric field in terms of this potential difference in length. So therefore, current is equal to sigma times potential over length times area. Now if I compare this expression with Ohm's law, maybe write it a little bit differently. You have V is equal to I times L over sigma A. And this is a resistance. Okay? So you see how the resistance is determined. It's a function not only of the material in question, it's a function of the geometry too. So the longer the wire is, the greater the resistance, and conversely, the bigger the cross-sectional area, the smaller the resistance as well. Okay, well, when we were talking about electrostatics, a point that we hammered home over and over again was the fact that the electric field vanishes inside of conductors. Well, that's no longer the case because we're not dealing with stationary charges anymore. We're dealing with charges in motion. And furthermore, we're dealing with systems where there's not perfect conductivity. Imperfect conductors, and also charges are in motion. So now we have a non-vanishing electric field inside. To give you an idea of the magnitudes of conductivities, let me write it up here. Let's say we've got silver, copper, and aluminum. And we'll throw water in there as well. For conductors such as silver, copper, and aluminum, they're all in the order of 10 to the 7th. And for water, that's on the order of 10 to the -6, which is an insulator. Copper is a good choice between both of these metals. It's not outrageously expensive. It's more expensive than aluminum, but it has very high conductivity. Some households in the U.S. are wired, and I imagine the rest of the world as well, are wired in aluminum, which is really not a good idea because they're not able to bear the amount of aluminum is not able to bear the amount of current that copper is. So anyway, if you're in good shape, your house is wired in copper. Let's take a look at another example. Let's suppose that you have two coaxial cylinders. And they're filled with material of conductivity sigma. I'm going to determine a couple of things here. I want to figure out the current that flows. I want to figure out the electric field. I want to figure out the resistance. Okay? So how do I write down the electric field? Well, if the coaxial cylinder inside bears uniform line charge density, then the electric field in the region between the two cylinders is the same as it's always been. It's lambda over 2 pi epsilon naught s, where s is the distance in the radial direction, the distance from the axis, and your electric field is in the radial direction. So I'm going to determine the potential difference between both of these. So we'll have an inner radius RA and an outer radius, the outer cylinder RB. Well, we know the drill, calculate the potential. If you know what the electric field is, that's just the line integral. From the reference point to some arbitrary point. So, and therefore we'll wind up with minus lambda over 2 pi epsilon naught take the minus sign out of there, times natural log of RB over RA. Okay, what about the current? Well, in this case, we can't just take the product of the volume current density in the area because volume current density is not going to be uniform in between. It's basically just sigma times the electric field down into the normal. Evaluate the current that flows out through some area. That is equal to sigma times lambda times L over epsilon naught to determine the resistance of the material between the two cylinders. We just apply Ohm's law, and therefore R is equal to V over I. Epsilon naught cancels, lambda cancels. And we wind up with the resistance of the system is 1 over 2 pi sigma length of the cylinders times the natural log of the outside radius over the inner radius. So natural log of RB over RA. And by the way, people often speak of the resistivity. A lot of people use the character rho to represent resistivity. Other people use the character eta for resistivity. Rho is kind of overused in my opinion, so we'll stick with the resistivity, designated by eta. Okay, so the relation between conductivity and resistivity, well, sigma is equal to 1 over eta. Now that we've looked over a few examples where we've calculated the current and the resistance, let's look at some basic circuit problems and solve those and point out some, or make some observations about some things that may have bothered you when you first started learning about circuits and then learned to basically put aside, and you shouldn't have, because if you had these certain ideas, you were onto something. Okay. So let me very quickly make the case that the electric field is uniform inside. Well, we have Ohm's law. And we have steady currents. The divergence of the current density vanishes. So this is for steady currents. And therefore, the divergence of the electric field must also vanish. Well, if the divergence of the electric field vanishes, we can actually define a potential in that case, and electric field is just equal to minus the gradient of the potential, and therefore Ohm's law, or excuse me, Laplace's equation is satisfied. So you know the drill with doing boundary value problems. Just come up with any solution that satisfies Laplace's equation in the boundary conditions, and that's your solution. That's what the uniqueness theorem guarantees. So if you want to come up with an expression for the potential, you can just write one down really easily, and I'll write this as cursive lowercase l. If I choose my potential to have the form V naught C over L, that certainly satisfies Laplace's equation. It also satisfies the boundary conditions too, because potential vanishes at V equals 0 and it's equal to V naught at Z equals L. So therefore, electric field is uniform inside. Okay, so we're talking about resistors. Let's talk about a circuit that's comprised of a battery and resistors. is our simple resistive circuit. It's comprised of a battery, you know, maybe providing 6 volts, and 2 resistors, R1 and R2, hooked up in series. So probably about the easiest circuit, resistive circuit you can encounter. And one way of proceeding, while you observe that these 2 resistors are in series with each other, therefore their equivalent resistance is just equal to R1 plus R2. And typically you want to figure out such things as what current's drawn, and we'll just leave that, generally speaking, as EMF. So therefore the current that's drawn is equal to the EMF provided by the battery divided by equivalent resistance of the circuit, or E over R1 plus R2. And the current that flows through R1 is the same as the current flows through R2. However, the potential differences are different. Potential drop across R1 is just equal to the current that flows through it times its resistance. And a similar expression for the potential drop across R2. That's just going to be EMF times R2 over R1 plus R2. And if you add these two up, you see that the potential drop over R1 and R2 is equal to the voltage supplied by the battery. And remember, EMF is that influence that carries charges from lower potential to higher potential. That's one way of defining it. Carry, or maybe drives is a better word, way of expressing that. Okay, so one of the things that may have bothered you, or you thought of when you first started doing circuits, is you might have asked yourself, well, gee, why do you draw it like this? Why not draw it like a circle? And then once you learn a little bit, you realize, okay, these hookup wires are equal potentials. You're basically treating them as equal potentials. They're perfect conductors, so there's no drop across here. You've got your 2 resistors, so it doesn't make any difference what the shape of this circuit looks like, and eventually you come to the conclusion, well, it's for aesthetic reasons. And yes, as far as circuit analysis goes, that's Jim Dandy. We also looked at transient circuits. As long as your battery is providing 6 volts, 12 volts, or whatever, you're going to have current flowing. Transient circuits, not so. Transient circuits contain such components as capacitors and or inductors. Transient meaning your current flows for a certain amount of time and eventually dies out. Capacitors, inductors, resistors are all called passive elements. What that means is that they don't provide more than average power over 0 over an infinite amount of time. Batteries, of course, are active elements because they are providing power. We haven't talked about inductors yet, so we're going to have to limit the discussion to capacitors for now. And the first circuit I'm going to look at is when we've got a capacitor, characterized by capacitance C, hooked up to some resistor. Well, this capacitor is going to be charged initially such that it has potential difference V naught. First thing I'm going to point out here, making a connection between field theory and circuits, is that you get a conduction current flowing towards one of the plates, but it doesn't appear that the conduction current actually flows in the internal circuit, if you will. And James Clerk Maxwell hypothesized the existence of a displacement current. And basically using Gauss rules to solve these problems. And if you just consider the conduction current, it's not immediately obvious that Kirchhoff's rule applies to this situation. But if you have a displacement current, and the displacement current actually has the same value as the conduction current, well, we can just say, well, the current's going to be continuous, and therefore we can still apply Kirchhoff's rules. I will be talking about the displacement current in much more detail in an upcoming lecture, and also tying everything together in Maxwell's equations. Okay, so that's a little bit of field theory becoming salient, if you will, in circuit analysis. But the answer here is, for our purposes, we can assume that, since we can assume that the current's continuous, we can, forget about that for now and just solve this problem. Okay, so Kirchhoff's rules. Solve that without really making it explicit. There are two rules: Kirchhoff's current rule, which tells you that the algebraic sum of the current into any node must vanish. And Kirchhoff's voltage rule. The algebraic sum of the voltage around the loop must be 0. Okay. And if you are taking any electrical engineering classes on circuit analysis, you've gotten into things like Norton's theorem, Thevenin's theorem, both of which are used to simplify complicated networks down into much simpler problems. And anyway, it's just like this, and recall that and since I is just equal to the amount of charge transported per unit time, start with some initial amount of charge Q naught on the capacitor, and at some future point, you're only going to have charge Q. So this becomes and as you can see, as time goes to infinity, the amount of charge goes to 0 on the capacitor. can determine what the current is by taking the time derivative. And that's equal to minus Q naught over RC times e to the minus t over RC. There's a certain amount of energy initially stored in the capacitor. It's equal to 1/2 capacitance times V naught squared, the initial potential. That energy is going somewhere. Well, it's flowing through, the current's flowing through the resistor, and that power is being dissipated in the form of heat. The amount of power is equal to I squared R. I want to show that the amount of energy dissipated in the resistor is equal to the amount of energy that was initially stored in the capacitor. And here we're going to integrate from time equals 0 to infinity. And squaring that's equal to Q naught squared over R squared C squared e to the minus 2t over RC dt. And since I wrote this as a potential, it's convenient to express this in terms of the initial potential V naught as well. And also times resistance as well. So we've got I squared times R, and that takes care of one of the R's in the denominator. When I evaluate the exponential at infinity, that of course gives me 0. And when I evaluate this at time 0, it just gives me 1. So because we got a minus here, from this factor we got minus minus, which is a plus, so this R cancels with this one, and we will be left with CV naught squared over 2. So in fact, the amount of energy that is dissipated in the resistor during the discharge process is equal to the amount of energy that was initially stored in the capacitor. Okay, so let's look at a charging circuit next. Okay, so now we have a discharging circuit, and we have a battery that provides EMF hooked up to a capacitor and to a resistor. So write down the voltages around the loop. We have minus V naught from the battery plus Q over C, the voltage across the capacitor, plus the voltage across the resistor. It's convenient to solve this as charge as a function of time. So remembering that I is equal to the time derivative of the charge, or the amount of time charge is transported per unit time, this is equal to minus V naught plus Q over C plus resistance times dQ by dt. I'm going to combine all the Q terms over to one side and all the time terms over to the right-hand side and integrate. First, I'll isolate dQ by dt. So we'll have dQ over Q minus CV naught. Integrate that. And over the right-hand side, that is going to be equal to minus dt over RC. So I swapped these signs over here, and of course that led to another minus sign. I integrate this. This is just natural log of Q minus CV naught. And we're going to go from time 0 to some final time t. And we want to go from no charge up to some charge Q. And it's minus natural log of minus CV naught. And that's equal to minus T over RC. Taking an exponential of both sides. And multiplying through by minus CV naught and then pulling this term over to the right-hand side, we wind up with CV naught, 1 minus e to the minus t over RC. And I want to figure out what current flows. That's just dQ by dt. First term just differentiates to 0, it's a constant. And the second term we wind up with V naught over R e to the minus t over RC. So again, as time goes to infinity, the amount of current that flows goes to 0. So basically what happens is once the capacitor is charged up, no more current flows. Okay, so we've looked at two different kinds of circuits. We've looked at a purely resistive circuit, and then we looked at a circuit that has a transient circuit. First case, discharging. Second case, charging. And we didn't really get into the field theory other than note that there has to be a displacement current in the capacitor, or that carries the current. So how does field theory relate to this? Okay, let's look at some questions that may have troubled you when you were first learning about circuits. First one of which is, does it matter? How you draw a circuit? Again, a very simple resistive circuit with one battery and one resistor, and you know, people don't draw it like this. And you thought, okay, once you start learning how to solve these problems using Kirchhoff's loop rules, you think, oh, it doesn't matter, right, according to circuit analysis, because you treat the wires, the hookup wires, as equal potentials. And I was thinking though, well, gee, now that we know ohmic devices also obey this expression, in other words, a long current density is equal to the conductivity times the electric field, I might think to yourself, well, gee, if the current is actually, or the circuit is laid out actually as I've drawn it, so in other words, the hookup wires are going up to the right, down, and so forth, the electric field also has to be changing inside as well. And in that case, electric field is going to be turning a different way from here over here. As I said, as far as circuits go, circuit analysis goes, it doesn't make any difference. But as far as field theory goes, there's a little bit of an issue there. Okay, so first question, does it matter? If you're talking about circuits, strictly speaking, circuit analysis, the answer is no. When you start wondering about the fields, though, it does make a difference. Okay, so number 2, when do Kirchhoff's rules apply or hold? And the answer is rigorously for DC. But as it turns out, they also hold for AC with negligible error. As long as you're talking about slowly varying currents. Okay? So definitely not for radio frequencies. You probably discuss this when you're talking about circuits, okay? So we'll put number 3. What drives the current? Well, your answer would be, well, battery, of course. It's giving juice to the battery, or juice to the circuit, right? That's not really a good enough answer. The answer is there are fields that are actually responsible for driving the current. And there's been some rekindled interest in this topic of late, so I will flesh this answer out in a little bit more detail. The question is, how fast does a current flow? Again, if you look at Ohm's law, there's an electric field inside. So you think to yourself, well, gee, the charges are continuously being accelerated, but they're not going to go faster and faster because they suffer collisions. So in fact, there's a mean drift velocity and that has value somewhere in the order of magnitude of 10 to the minus 4th meters per second. So that begs another question. When you flip on the light switch, why does it take forever for the lights to come on? Why do the lights come on almost instantaneously? After you flipped on the switch. And number 6, how is energy transported or power transferred in an AC circuit? And you might have been told, well, gee, it's because no matter which way it's going, the potential and the current have the same sign, so there is a net power transfer. That, as it turns out, is actually not a really good answer either, okay? So all these things that, you know, start thinking about circuits in a little bit more detail seems like a perplexing problem. And the answer to these questions really lies in the fact that surface charges appear. On circuits. And this has been known certainly since the time of Arnold Sommerfeld. And there have been a few papers published back in the 60s and 70s that dealt with this. And there's rekindled interest of late. And I have some really good articles listed on the BocaPhysics website. And there are varying degrees of difficulty. Some of them don't have a lot of math and it's just a nice white read, and other of them are, a few of them are at graduate level, I would say. Okay? So anyway, let's look at this surface charge business in a little bit more detail, but still qualitatively. Back in the 1960s, a researcher by the name of Rosser addressed this issue. And he presented his system like such. You've got your conducting wires, and the electric field flows to the right in the upper leg, and then it flows down in the lower leg. So something's responsible for turning the electric field. So what is that? Well, surface charges, okay? I'm going to first estimate the magnitude of the electric field inside of wire. To make this problem more concrete, we'll specify that we are talking about gauge 10 copper wire. And the reason why is because that's the kind of wire that's used in households. You recall about gauges, the lower the gauge, the thicker the wire. So gauge 10 wire has diameter 2.59 millimeters. Gauge 36. Double check myself on those figures. That's 0.13 millimeters in diameter. Okay? So how do I figure out what the electric field is? Just apply Gauss's law. Or rather, I should say, just apply Ohm's law, and then we'll make use of Gauss's law to figure out what the charge is. Okay, so first of all, we're going to determine what the electric field is. That's J over sigma. And J is just the current, or the cross-sectional area, times sigma. Okay, let's suppose that we are dealing with wire that carries 1 amp. And the area here is going to be pi times 0.00259 divided by 2 squared. Since we were talking about copper, the conductivity is 5.81 times 10 to the 7th. wind up with 0.0033 volts per meter. Now, that's a very small electric field, and which stands to reason because copper is a very good conductor. And unfortunately, I'm going to have to erase this as well. Now, if I want to apply Gauss's law, let's take another example. Let's suppose that you've got 100 amps being carried by a wire. And I'm going to determine how much surface charge is necessary to turn the field. So here we were just looking at 1 amp being carried by the wire, but now I'm going to go up to 100 amps carried by the wire. So Q is equal to epsilon naught EA, and the electric field is equal to the volume current density over sigma times A, and that's just equal to permittivity of free space epsilon naught times the current over sigma. So we have 100 amps carried by the wire. In the order of 1.5 times 10 minus 17 coulombs, or in the neighborhood of 100 electrons. So that's really very little charge, considering the amount of current that's basically being turned. Okay, so venerable J.D. Jackson in a 1996 paper identified 3 roles that surface charges play. First one is to maintain potential difference, or potential around the circuit. Second role that they play is to provide electric field outside of the circuit. And the third role that they play is to confine charge to circuit. Okay, so we pose the question, what drives the current? Well, it's the surface charges that give rise to an electric field that confine the charges to the circuit, and also enables the current to turn, enables it to bend. Okay? I'm going to talk a little bit more about the electric field outside of the circuit. And for that, We're going to reference a paper written by Mark Heald. Back in 1984. And basically what he did was to instead of drawing his circuit like a normal rectangle, he draws it as a circle. And then he also looked at a problem where he assumed the resistor was distributed around the circuit. And he treated this problem two-dimensionally. By two dimensions, I don't mean that he just looked at it like a circuit laid out on a laboratory bench. What I mean is that he envisioned this as a stack, an infinite stack of circuits. And by doing that, we've got current flowing, you can assume that it's flowing azimuthally. In fact, it's a current sheet now, not just a current flowing through the wires. Well, if that's the case, that makes the magnetic field really easy to solve. A magnetic field that is uniform inside and vanishes outside. Now, what about the electric field? Well, we already discussed this, that Laplace's equation holds. So basically, you can treat this as a boundary value problem. Usually envision a battery just to be really skinny little piece here, okay? Look at two problems, one with a lump resistor and one with a distributed resistor. Laplace's equation holds, so this means it's just a garden variety boundary value problem in electrostatics. Once you know what the potential is, you can solve for the electric field. So once you know the electric field, once you know the magnetic field, that enables you to calculate the Poynting flux. And the risk of getting too far ahead of myself in the lecture, because we don't get into this for another few weeks. Poynting flux is defined as the cross product of the electric field and magnetic field divided by the permeability of free space. And probably talked about it in your class, general physics class. Poynting flux is the energy transported per unit time, per unit area. So the very cool thing is, when you do these calculations, what you see here is that the energy is actually transported outside of the wires, not through the wires. You might have thought, well, the energy is being carried by the current, right? Not so. It's the fields that carry the energy. And so when I pose the question, why is it when I flip a light switch on, doesn't it take seconds or minutes for the lights to come on? because the mean drift velocity of the charge carriers is very low. It's very small, okay? But the fact of it is, the energy is not carried by the current, it's carried by the fields. And the fields are outside the wires, and that's why fields travel close to the speed of light. And that's why the lights come on almost instantaneously rather than at a snail's pace. So this is the neat thing, I think. Electromagnetic energy transported outside of wires. And the way Heald characterizes it is that the wires serve as railroad tracks. And it's surface charges that make this possible. So this is a two-dimensional case, and you will see, if you think about this too, there's a little bit of an approximation involved here, because clearly the electric field, magnetic fields aren't going to vanish outside. So some people over the past few years have actually come up with a way of treating resistive wires toroidal shaped, and they've looked at the Poynting flux due to those systems. In fact, J.D. Jackson was the first person, though, I believe, who came up with, did these kinds of calculations on a system consisting or comprised of finite currents. Okay? So the big thing here, big answer, it's surface charges that appear in the circuits. They give rise to electric fields that actually drive the current around the circuit. And as far as energy being transported, that takes place outside of the wires. I mean, it's not inside, and it takes some convincing to accept that that's what happens. But clearly, if you look at or AC circuits, for instance, and you think to yourself, well, it's being carried by the current. No, it's carried by the fields. Okay. So let's wrap today's lecture up with definition of EMF. And force per unit charge, well, you got the source, and you got your electrostatic field. EMF is defined as the line integral of the force per unit charge around the circuit. Well, just like before, the line integral of an electrostatic field around a closed circuit vanishes, so that term just drops out, and we are left with the EMF is equal to the force per unit charge by the source, and the line integral of the force per unit charge around the circuit. And the source in this case is a battery. It might be a generator. Generally speaking, it's localized to where the battery actual moving parts are. And next lecture we will be talking about motional EMF and calculating such things as the EMF due to the changing flux. Okay, so that concludes today's lecture.